All right. So today we're going to start a new topic. And the topic is, finally, we will be moving on to differential equations with variable coefficients, ODEs, with variable coefficients. Okay. And having disposed of higher order ODEs in the last two lectures, we will get back again to the case of second order. So my goal is to try and illustrate a very powerful and very widely used technique to solve second order differential equations with variable coefficients. I mean equations of this sort. Q of xy equals R of x. Okay, so as usual, we'll start with the homogeneous equation, y double prime plus p of xy prime plus q of xy equals 0, and then we'll move on to the inhomogeneous stuff. So the homogeneous part is y double prime plus p of xy prime plus q of xy equals 0. Okay, of course, you can make this equation into an initial value problem by specifying y at x0 to be some value and y prime at x0 to be some value. Okay, and of course, you guys know by now that this initial value problem has a unique solution as long as the functions p, q, and r are continuous in some open interval. Okay. Okay, so I'm trying to. All right. So now the question is, by now we know and we have learned a couple of methods to solve these equations if p and q are constants, right? So you guys know how to get the solution for such equations. And now we want to move on to the case of p and q being actual functions of x. Okay. And we want to understand a type of solution method called solution by power series. Or this is also called series solution method, which is what I'm used to calling it. Okay. So there are conditions under which this applies. There has to be certain conditions on P and Q, and we will certainly come to them. But first, I want to illustrate what this does for you. Okay, so by giving you a couple of examples and walking you through equations for which you already know the solution, because I need to convince you that this stuff is not hocus pocus, it actually works. So I will convince you by giving a couple of examples of equations that you already know how to solve constant coefficient problems using the power series method. And then we will generalize this method to variable coefficient problems. And in the meanwhile, I will also tell you a few words about the validity of this method and in what conditions it is applicable and so on and so forth. Okay. So let us begin at the beginning. So what is the power series method? What is the power series? Excuse me. So you have seen many kinds of power series representations, right? So as long as I'm able to express any function f of x as some am x minus x0 m, then this function f of x is said to have a power series representation. Okay. So x0, this is just jargon. This is called the center of the series. In many cases, we will be looking at expansions around x0 is equals 0, in which case this becomes m equals 0 to infinity am x to the m. Okay, so let's call this equation 1. So you've seen many examples of this sort, and I don't want to belabor this point because it might be too trivial for you. For example, you know by now that e to the x, for example, can be written as 1 plus x squared over 2 factorial plus so on and so forth. Okay. And you can also write this in this compact notation, m equals 0 to infinity, x to the m over m factorial. Okay, and this compact notation will be very useful for us while we solve certain problems. For example, sine x would be x minus x cubed by 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial and so on. So this can also be written as a series. So we have to account for the fact that there is only odd powers of x, and we also have to account for the fact that the sign of each term keeps alternating. So let us put, first of all, let us write down an x to the 2m plus 1, okay, because the series starts at x and only has odd powers. And the denominator is the same factorial as the power. So this is 2m plus 1 factorial. And to account for the fact that each term has an alternating sign, I multiply by minus 1 to the. And similarly, you can write down series expansions. For example, you also know the geometric series, right? 1 minus x can be written as 1 plus x squared plus blah, blah, blah. Your familiar Taylor series and Maclaurin series and all these things are examples of power series. So we want to understand the solution of second order differential equations, variable coefficients, where y of x can be represented as a power series. Now, this power series may or may not be a power series that you have seen already. For example, there could be solutions where the solution is just sine and cosine, and these power series are stuff that you have already seen. In fact, we will start with this example today. But there is also more powerful power series in physics and engineering problems that are very widely used. For example, you have actually seen a couple in your quantum mechanics class in the first semester, right? So when you did harmonic oscillator, you studied what are called Hermite polynomials. Hermite polynomials are not some random things that mathematicians invented. They are the solutions of a particular differential equation called Hermite's differential equation. There are so-called Legendre polynomials. There is Legendre polynomials. We will understand Legendre polynomials starting next week. So these are all very useful in many problems. For example, Legendre polynomials appear in any problem that has a spherical symmetry. Okay, so you guys will see it in many engineering applications also. So we want to understand the general series solution method applicable for such problems. And as a warm-up today, I will explain how the series solution works for some very simple problems which you have seen already. Okay. So this is a warm-up exercise. Example 1. Suppose I give you the differential equation y prime equals y. Okay, this is a trivial differential equation that you know how to solve. You simply integrate both sides, right? So dy by y equals dx, which gives you y of x is e to the x, some a e to the x. And you can always determine this a by appearing to initial value conditions. Okay, so you really don't need a power series method to solve this, but I want to take this simple example and another simple example to illustrate how the method works. Any questions? Now, what am I saying? I'm saying that suppose if I'm only given this differential equation, I will start by positing that the solution of this differential equation can be written down as a series in x. Y of x equals m equals 0 to infinity am x to the m. Okay. Now my goal is to find the AMs. How many AMs are there? Well, infinite number of them, because each power of x has a different coefficient. So on the face of it, this looks like an impossible problem, because I am basically saying that the solution is a power series in x. I have to determine all the coefficients to determine this power series, but there is an infinite number of coefficients and I have only one equation. So how am I going to determine all of them? Okay. So on the face of it, this looks like a problem that will never work, an idea that will never work, but it does work in a very beautiful way, as you will see. So I will write this power series in a grotesque expanded form: a0 plus a1x plus a2x squared plus a3x cubed plus so on and so forth. And just for this problem, I'll work with this expanded series instead of this compact notation, because I want to show you how it works. And I also want to impress upon you the power of using the compact notation. You will go mad if you use the entire series every time you want to solve a problem. Okay, so this is my onsorts. My onsorts is that the solution for this problem can be written down as a series in X. Okay, now somebody will come and say, okay, so what are the coefficients? So let us go ahead and find what the coefficients are. So if this is my y, what is my y prime of X? Well, since it's a linear sum, ddx of this series is just ddx of the first term plus the ddx of the second term and so on and so forth. ddx of the first term is 0. I'm going very slow initially, so if you have any questions at any point, I'm guessing that you have not seen this before, so please stop me. ddx of the first term is obviously 0 because a0 is just a constant. So this gives me a1 plus 2a2x plus 3a3x squared plus obviously 4a to the 4x cubed and so on and so forth. Okay. So the point is that this y of x solves this differential equation y prime minus y equals 0, which is what y prime equals y is. So let us substitute what y prime is and what y is. What is y prime? Y prime is a1 plus 2a2x plus 3a3x squared plus blah, 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 minus a0 plus a1x plus a2x squared plus a3x cubed plus blah, blah, blah. This equals 0. Okay. Now here comes the important part. So this is a first order differential equation. I have one series for y prime and one series for y. But of course, now that I've written everything down as a series, and there is no differentiations or anything like that, I can write this as just one series. I can combine all the terms and I can write this as just one series, because after all, the first series is just some series in X, something times X squared and so on and so forth. The second series is also the exact same thing. So I'll combine the coefficients of powers of X. For example, the first term from this series is A1. The first term from the second series is minus A0. The coefficient of X from the first term is 2A2. The coefficient of X from the second term is minus A1. Plus the coefficient of X squared from the first term is 3A3. The coefficient of X squared from the second term is minus A2. And you can easily guess that this would be 4a4 minus a3 x cubed and so on and so forth. And the whole thing is equal to 0. It's equal to 0 because by assumption, my 0 is turning out very weird today. By assumption, this series solves the differential equation. That is what I've assumed. Okay. I have no basis for assuming this because I would tell you why I would even think of something so crazy as this. But again, my first goal here is to try and tell you how this works and then tell you under what conditions it works. Any questions or any comments up till now? So does this equation make sense? On the left-hand side, you have a series in X, and the right-hand side, you have this whole series sums to a 0. This infinite series sums to 0. So under what condition can this equation be valid?
All coefficients are 0.
All coefficients have to be 0. If it is a finite series, I have hope, right? If it is a finite series, I have a hope that maybe the 6th term will cancel the 2nd term, and the 5th term will cancel the 3rd term, and so on and so forth. There can be some other ideas. But if it is an infinite series, there is no way I can hope that one term can cancel the other term because they are all different powers of X. And if I put X is equal to some value, there is no reason to assume that these terms will individually cancel each other. The only way I can ensure that this series is 0 is if every coefficient of every power of X is 0. So I'll write this down explicitly. Every coefficient of every power of x is 0. That's the only way in which I can make sense out of this equation. So what does this give me? Well, let us equate all the coefficients of all powers of x to 0. I get a1 minus a0 equals 0. Okay, so which tells me that a1, the first coefficient, is the same, sorry, the second coefficient is the same as the leading order coefficient a0. The second term tells me that 2a2 minus a1 equals 0. Okay, this tells me a2 is 1/2 a1. But I also know that a1 is the same as a0, so I can write this as 1/2 a0. Okay, so you see a pattern emerging. Even though we started with what seemed like an impossible problem where we had to determine an infinite number of coefficients, there is some relationship between the coefficients imposed by this series. Because this series equals the sum equals 0, I always can demand that the individual coefficients have to be 0. This is a pattern that will repeat in all these problems. So please pay attention in this simple case. So let us actually go ahead and work out at least one more. The third coefficient for x, a square, is 3a3 minus a2. This has to be equal to 0, which tells me that a3 has to be 1/3 of a2. Okay. But I also know that a2 is 1/2 of a0, so I can write this as 1/3 times 1/2, and just for shits and giggles, I'll write this as 1/1 times a0. Okay. So you see that this can be written as 1/2 factorial times a0, and this can be written as 1/3 factorial times a0. Okay. So just to make absolutely sure, this next term is 4a4 minus a3 equals 0, which tells me a4 is 1/4 of a3, but a3 itself is 1/3 factorial a0, which means a4 is 1/4 factorial a0. Okay, so which tells me that even though I started with an infinite number of coefficients, I really don't have infinite number of coefficients after all, because once I know what a0 is, I can fix everything else in terms of a0. So this idea that once you know a finite number of coefficients, you can determine the other coefficients in terms of this finite number of coefficients is a very powerful idea. And these relations are called recursion relations. Between the AMs. So in this particular problem, how many coefficients do I really need to determine all of them? Well, I only need to fix a0. Is that consistent? Of course it is consistent, because I'm solving a first order differential equation. A first order differential equation always has one constant. So in the direct integration case, I chose this constant as a. In the power series case, I will choose this as the leading constant a0. Okay, so I'll determine everything else in terms of a0. So what is the solution to my problem? The solution to my problem is y of x equals a0 plus a1x plus a2x squared plus so on and so forth, plus a3x cubed plus so on and so forth, right? And this is equal to a0 plus a0x plus 1/2 factorial a0x squared plus 1/3 factorial a0x cubed, and so on and so forth. And this can be obviously written as a very neat power series, a power series that actually sums to something that is very familiar. Okay, so y of x in this case is just a0 e to the x. You might argue that this is a crazy way to do the problem, because you can get this in one step, and you're absolutely correct. Okay, this is indeed a crazy way to do the problem. But the reason I am doing this out in detail, and I'm also going to do a second problem out in detail, is because I want to show you how this works. So the first step is to write down your on source for the problem, which is a power series, and then figure out the first derivative of this power series. in case you have only a first order differential equation, and then substitute the derivative and the expression for y in the differential equation, get a recursion relation between the coefficients, and use this recursion relation to solve the coefficients. And in this case, because it's a first order differential equation, you have only one undetermined coefficients. It turns out that you can determine everything else using this one coefficient. Okay. So this is how the power series works. Before I move on to the second example, which is again something that you know how to solve, are there any questions about any of this? Any questions or any comments that anybody have? Okay. So the second example is again something that you have seen before, y double prime plus omega square y equals 0. Okay. And again, you should stop me and tell me that you know how to solve this already. And you're right. The solution obviously is a cosine omega x plus b sine omega x. But I want to explain the methodology in the second order case also. Okay. So again, I will start the exact same way I started before. I will assume that the solution for this guy, whatever the solution is, for now, I'll pretend that I don't know what the solution is. So I'll pretend that y of x can be written as some power series am x to the m. Okay. And now I want to introduce to you a shorthand notation to solve these problems. So in the first problem, we wrote everything down in terms of all these different terms, and then we explicitly looked at all these different terms. This can be a little cumbersome if your equation is a little complicated. So let us actually write down a simpler way of looking at y prime and y double prime and so on and so forth. So after all, this is a series, right? So if I differentiate this series, I will differentiate this term by term, because ddx of f of x plus g of x is just f prime plus g prime. I differentiate each guy and just add up those terms, right? So this is a trivial thing. So since this is a power series and each term can be differentiated individually and added, I can write y prime in one fell swoop as ddx of m equals 0 to infinity amx to the m. And it doesn't matter if I differentiate and then add. So I'll write this as m equals 0 to infinity ddx of amx to the m. And since am's are just constants, this simply becomes m equals 0 to infinity am mx to the m minus 1. Okay, so this is again a series, but this series is a slightly different series. It has x to the m minus 1. Okay. Oh, by the way, I should tell you one quick thing before we move on, but I will tell you that after I solve this problem. Okay. So I'm also assuming here that I'm not looking at any fractional powers of x. So when I look at a power series, I can also look at fractional powers of x or inverse powers of x. When I claim that I'm solving using a power series method, I'm actually claiming that m is an integer greater than m is a positive integer. Okay. So I'll assume for now that we will look at the fractional case later. For now, I will assume that m is not a fractional integer, or it's not negative also. Okay. So sorry, I should have told you this at the very beginning. So if you look at a power series like this, y prime, now the first term in y is obviously a0, but the first term in y prime is not m equals 0. Okay, automatically the m equal to 0 term vanishes. So I don't have any fractional powers of x or inverse powers of x, because the m equals 0 term, since it's multiplied by m, is equal to 0. So again, the first term in this series is only a1. So if I can write y as a0 plus a1x plus a2x squared and so on and so forth, I can write y prime as m equals 0 is just 0. So m equals 1 is x to the 0, which is 1, plus a2x plus a3x squared and so on and so forth. Okay, so compare this series and this series, you find that the coefficient of x is a1 in this case, but it is a2 in the second case. The coefficient of x squared is a2 in the first case, but it's a3 in the second case. That's because the differentiation has brought down 1 power of x. Okay, so this is important to know. Similarly, what is y double prime? Y double prime would be ddx of y prime, which I can write again as m equals 0 to infinity, m minus 1, sorry, am m minus 1 x to the m minus 2. Okay, so again, you don't have to worry that there can be powers of minus 1 and minus 2 here, because this series vanishes for both m equals 0 and m equals 1. So if I write the series out in detail, this looks like m equal to 0 is 0, m equals 1 is 0. So this series starts at a2, and a2 has 0 powers of x, so it's a constant. A3x plus a4x squared, and so on and so forth. Okay. So, but if you actually look at these guys, the y of x, y prime of x, and y double prime of x, they are all a simple series in x. It has coefficients of x to the 0, x to the 1, x to the 2, x to the 3, and so on and so forth. But the order of the coefficients has shifted by 1 unit and 2 units, right? So in the first case, I had a0 plus a1x. In the second case, I have a1 plus a2. The third case, it is again shifted by 2 units. I have a2 plus a3x, and so on and so forth. So let us go back to the differential equation. Y double prime plus omega square y equals 0. Okay, so this I will write as m equals 0 to infinity am m minus 1 x to the m minus 2 plus omega square m equals 0 to infinity am x to the m equals 0. Okay, now again, I want to do the essentially exact same trick as the first order problem. I want to write this series as some constant plus something times x plus something times x squared, and so on and so forth. So I have to do this comparing the y double prime series and the y series, but the y double prime series, as I have told you now, is shifted by 2 units, right? Sorry, 2 units is a very confusing terminology, but what I mean is that it is down by 2 powers of x. So this guy starts at a0, this guy starts at a2. So an easy way to deal with this in this shorthand notation is to look at this first term, right? And then since this is an infinite series after all, I can make any substitutions in m. So I will make the substitution m goes to m plus 2. Okay. So if I make the substitution m goes to m plus 2, what do I get? So the first series becomes a m plus 2, m becomes m plus 2, and m minus 1 becomes m plus 1. Okay, and this becomes x to the m, because m minus 2 plus 2 is equal to 0. The second series is obviously am x to the m. I leave it untouched. So the only difference between the first equation and the second, this step and this step, is that I've relabeled m as m plus 2. You don't have to do this if you're going to do it out this way. So the way we did the first problem, if I explicitly write out every coefficient, I don't have to do it this way, but it is a little cumbersome to write it this way. So this is a useful trick to follow. Again, when it comes to variable coefficients, you should always try to get the equation such that something times x to the m is equal to 0. And the way you can adjust this, for example, you can also have a y prime term in the differential equation. In this example, we do not. But since we have variable coefficients, it can also be multiplied by some power of x, like x cubed or x to the 4th, right? So how you adjust this series will become important. In this case, what works is a substitution m goes to m plus 2. So now the entire series becomes something like a m plus 2 times m plus 1 plus omega square am x to the m equals 0. Okay. So again, this is a power series in X, and the only way this power series can actually sum to 0, an infinite power series can sum to 0, is if each of these coefficients is equal to 0. By the way, if you're confused about this step of relabeling m to m plus 2, a good way to convince yourself is to actually write it out explicitly and prove to yourself that this is the same as the series before. So if I start at m equal to 0, this is basically, so this is obviously m equal to 0 to infinity. The first term is, of course, a2. 0 plus 2 is 2. 0 plus 1 is 1. X to the 0, which is first term is 2a2. Okay. So what is the first term in this series? M equal to 0 is 0. M equals 1 is also 0. The first term is obviously m equals 2. So it is 2. M is 2. 2 minus 1 is 1. And x to the 0. Okay. So the first term here is 2a2. The first term here is also 2a2. So this relabeling does not do anything to the series itself, except massage it into a more convenient form that we can easily manipulate. Okay. All right. So let us go ahead and solve this completely. So now this gives me a recursion relation between the coefficients. What is this recursion relation now? Recursion relation in this case is the following. am plus 2 equals minus omega square divided by m plus 1 times m plus 2 am. Okay. So now, if I know the first term, remember, this is slightly different, and I want you to appreciate this. This is slightly different from the first case. In the first case, once we knew a0, we could figure out a1. And once you knew a1, you could figure out a2. So once you knew a0, you could figure out the entire series. Okay. But supposing I know what a0 is, what I can figure out is, suppose if I put m equal to 0 on both sides of this equation, I can figure out a2 in terms of a0, right? So suppose you know a0. You want to take advantage of this. So let us put in a0 on both sides of this equation. So this equation becomes a2 equals minus omega square times 1 times 2 a0. How about a1? Well, I have no way of determining a1. Okay, but I know a2 from a0. So let me use the idea that I know a2 already and try to figure out a3. Well, I cannot, because if I plug in m equals 2 on this in this equation, I can figure out a4 in terms of a2, but there is no way to figure out a3. So let me at least figure out a4. So a4 would be minus omega square divided by, putting m equals to 2, I get 3 times 4 a2. Okay, and this would be omega to the 4th times 3 times 4 times 2 times 1 a0. Okay, so similarly, you can guess that a6 would be minus omega to the 6th over 6 factorial a0, and so on and so forth. Okay, so if I knew a0, I can figure out all the even coefficients by appealing to this recursion relations. What about the odd coefficients? Well, I don't know what the odd coefficients are. You should give me at least one to work with. Why? Because unlike the first problem, I'm doing a second order differential equations, and I need two constants. It should always be expressed as, the solution should always be expressed as one with two undetermined constants. The first constant that I've chosen here is a0 to generate all the even coefficients. So I'll also assume that a1 is given to me. Suppose you know a1, then I can appeal to the exact same recursion relation and figure out all the odd coefficients, because now a3, if I put m equals 1 in this equation, would be, excuse me, minus omega square divided by, if I put 1, I get 2 times 3 a1. a5, if I put m equals 3 in this equation, minus omega square divided by 4 times 5a3. Okay, and this would be omega to the 4 by 5 factorial a1. Okay, so once I fixed two constants in the second order differential case, I can generate all the other coefficients by appealing to the recursion relation. So let me write down the explicit solution. You might already guess what the solution is because you see the pattern emerging, but I will write it out anyway. So I will first collect all the even powers of x. So a0 has 0 powers of x, a2 has 2 powers of x, and so on and so forth. So I will write this series as a0 plus a2x squared plus a4x to the 4 and so on and so forth, plus, excuse me, a1 x plus a3x cubed plus a5x to the 5 and so on and so forth. Okay, so since all the even coefficients are determined in terms of a0, I can write this as y of x equals a0 times 1. a2 would be minus omega square over 2 factorial x square. a4 would be plus omega to the 4th x to the 4th over 4 factorial minus omega to the 6th x to the 6th over 6 factorial plus so on and so forth. Plus, if I pull out a1, what do I get? The first term would be just x. Okay. The second term excuse me. Just give me 1 second here. The second term is minus omega square x cubed over 3 factorial plus omega to the 4th x to the 5 over 5 factorial and so on and so forth, right? Now, since a1 is a constant, I can as well multiply the entire thing by omega, and I can write this as y of x equals a0 times 1 minus omega square x squared over 2 factorial plus so on and so forth, plus a1, where this a1 is of course, so let me call this a1 tilde, and this I will call a1, where a1 is just a1 tilde times omega. I've simply multiplied by omega. I can always do that because it's just an undetermined constant anyway. And I can write this as omega x minus omega cubed x cubed over 3 factorial plus omega to the 5 x to the 5 over 5 factorial and so on and so forth. And by such laborious means, you have figured out what you already knew, that this is a0 cosine omega x plus a1 sine omega x. Okay. So this is how a series solution in principle, in practice, actually not in principle, in practice works. You take the differential equation, substitute the onsorts, okay, figure out the series. In general, of course, you will have an equation like, let me go back to blue. In general, you would have y double prime plus p of x y prime plus q of x y equals 0, right? Assuming you don't have an r of x on the right hand side for now. Now, let us say p of x is x squared and q of x is x cubed, right? So suppose if my differential equation is x squared y prime plus x cubed y equal to 0, right? So how will I substitute the onsorts now? Again, I will say y is amx to the m, and the first series is am m minus 1, x to the m minus 2. The second guy, remember now it is not a constant that multiplies y prime, but a function of x, in particular x squared. So this is am m x to the m minus 1. The third term is, of course, am x to the m. Okay. So now you'll have to massage this series such that you collect all the coefficients of similar powers of x. The way to do this is, now I can shift m by m plus 2 and write this as x to the m. I can shift, but you might be tempted to shift m by m plus 1 here. If this was a constant, that will be completely right. But the second series is now actually, I can take this x square inside and write this as am x to the m plus 1. Okay, so now you have to be careful. The third series is actually am x to the m plus 3. Okay, so now to collect the coefficients, you have to shift the coefficients carefully. So we will do a couple of examples when we get there. But again, the methodology is the same. Once you have figured out how to collect the coefficients, you write down the recursion relations. And once you write down the recursion relations, you fix 2 in the case of a second order differential equation, and you can generate the rest. Okay, so this is how the series solution method works. Any questions or any comments about any of this thus far? Okay. So, okay, so I will erase this part because we're going to talk more about this in the next lecture. And I'll say a few words about series in general and stop for today. So suppose I write a series, right? Like m equals 0 to infinity, am x minus x0 to the m. Okay. Now, one of the things that you worry about is if the series is convergent or divergent, right? So suppose if you have the simple geometric series 1 plus x squared plus x cubed plus blah, 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 right? Now, if it sums to something very nice, you already know what the answer is. For example, if x is 0.5, the left-hand side is obviously finite. So the right-hand side, the series solution should also be finite. Now, which means you're adding an infinite number of terms. So in some loose sense, you already know that as you keep adding more and more and more terms, at some point they should stop becoming very important. Why? Because if x is equal to half, let us say, the left-hand side of this equation is 1 over 1/2, which is 2. Okay. Now look at the right-hand side. The right-hand side would be 1 plus 1/2 plus 1/2 squared plus 1/2 cubed and so on and so forth, right? So as a practical aspect, the first 3 terms add up to 1.75, right? So this is 1 plus 0.5 plus 0.25. So this is 1.75 plus 1/2 cubed plus 1/2 to the 4th and so on and so forth. And I don't really need an infinite number of terms to see that this is going to converge to some value. And that value in this case turns out to be 2 for this particular value of x. Now, if x is some other value, let us say 0.75, it will converge to a different value and I might need a few more terms. Now, if x is 5, okay, now it becomes interesting. Why? Because the left-hand side seemingly is diverging. So, but this is this is valid for any x, right? So this is a geometric series, and geometric series always sums to 1 minus. So if the leading term is just 1, it is 1 minus the ratio, and the ratio in this case is just x. So this is how you sum the series. So the series representation has to be taken a little carefully. You might have values of x in which the series converges, in which it is a faithful representation of whatever function you're choosing. But you could also be in a regime of x where the series just blows up, it diverges, in which case it will not be a faithful representation of whatever series that you're looking to represent. So this issue of convergence and divergence is important. Even though this is an exact sum geometric series wise, depending on what the value of x is, this series can have different properties. Okay, so we want to understand what these properties are in a slightly technical language. This is a very complicated issue. We won't go very deep into it, but I'll tell you a few words about how to approach this notion of convergence. Now, you should also notice again that this is a very simple series where all the coefficients of all powers of x is just 1. So I can have a more complicated series like, excuse me, a0 plus a1x plus a2x squared plus a3x cubed, and so on and so forth, where a0, a1, a2, a3 are all different from 1. Now, again, I can make a conclusion about the convergence based on x, right? So, for example, if x is 0.1, I can assume that this series will converge in some region of x. But of course, if the coefficients of this series keep increasing, then that is also not guaranteed to me, right? So there is two things to consider. One, the region in x in which a particular series converges, and two, the coefficients, what the absolute value of these coefficients are. For example, if these coefficients an is something like, n factorial to the power n or something crazy like this, then obviously as I keep adding higher and higher terms, the higher order terms start becoming more and more important, right? And this series might not converge. I do not know. So I'll have to pay attention to what my coefficients are also. So how will I look at these things in a slightly less vague language? So let us take a particular series, right? Let us take this series 1 plus x squared, because it is fairly simple enough. I will write more and more terms. Okay. So what do I mean by convergence? I want to walk you through this as a practical measure. So suppose if I take just the first term, okay, let us say that I approximate this series for the first term. Now, in general, that will be a bad approximation, right? Because if even the x term is not very important, then you don't even need a series representation. So perhaps only the first term is not a good approximation. So let me just keep it aside. So let me call this S0. S0 is the series truncated at the 0th power of x. Okay. So this is S0. Now let me add minimally. So let me add this, the first term. I'll call this S1. S1 is just 1 plus x plus higher powers of x. Similarly, I'll call this as S2 and S3 and so on and so forth. So by looking at this series, I want to understand convergence by claiming that at some point adding more and more terms is not going to buy you much. So to understand this in steps, I'm going to split this series into a series of sequences. The first sequence S0 has just the first term. The second sequence S1 has the first term and the second term. The third sequence has the first term, second term, and third term, and so on and so forth. So instead of looking at this series as an infinite series, I can look upon it as a excuse me, as a sequence of sequences, so to speak, right? S0, S1, S2, S3, and so on and so forth. Okay. Now I don't claim that if I add these sequences, I get this series. I don't, because if I add the sequences, I double count everything, triple count, whatever it is, right? So I don't mean that I'm going to add these series. I'm going to look at the sequences of these series. And I'm going to try and understand at what point in the sequence does adding more buy you less? Because that is what convergence really is. So let us actually throw a little more terminology at you. So in this particular series, S0 is just 1. Okay. Now, whatever remains, that is called the remainder. The remainder of the series is R0 is x plus x squared plus x cubed and so on and so forth. S1 of the series is 1 plus x, and R1 would be, I've taken 1 and x, so whatever remains is the remainder of this series. S2 is 1 plus x squared, and R2 is obviously x cubed plus x to the 4 and so on and so forth. Okay, so I can construct a whole bunch of sequences and the corresponding remainders to these sequences. Okay, so when I say the series converges, it means that if I keep looking at this sequence, right? So I know what S0 is in this case. S0 is just 1. Suppose if I fix the value of x to some value, let us say 0.5, I know what S1 is because it is 1 plus 0.5, which is 1.5. I know S2 is, I know what S3 is, right? So converging series is that series for which the limit of this sequence is a number that you already understand and you can sum. In other words, using the wrong color, convergent series. Okay, I'll give you the definition. If for some value of x equals x1, say, the list of sequences is such that limit n tends to infinity Sn of x1 is just some number to which the series converges. So what does this mean? So if for some value of x, in this case, again, I chose the example as 0.5, S0 is just 1, S1 is 1.5, S2 is 1.75, and S3 is, I don't know, something slightly more than 1.75, and so on and so forth, right? So I know that this series should converge to the number 2, because in this case, I actually know what it is. In general, I don't know what it is, but I can see the series converging to this particular number. So I can claim that if I add enough number of terms and I construct the sum of this sequence where n is some large number, let us say, in this case, even adding 4 numbers gets me some number like 1.8, which is pretty close to 2. But if I keep adding enough number of terms, I can get a very good approximation to my series. So, and this is a particular definite number. It's not blowing up. If I keep adding more terms, it doesn't blow up. And that is because I've chosen the value of x carefully, right? So if I look at this limit of sequences, the limit of sequences under a large enough number n, this sequence sums to a very definite number, some s of x1 in this case. So such a series is called a convergent series. It's a converging series because the sequences has a limit. The list of sequences has a limit such that the limit gives you the value or sum of the series. So this is the value or sum of the series. Of course, if such a thing cannot be found, and if you keep adding more and more terms, the higher and higher order terms start contributing more and more, then you have what is called a divergent series. But we will stick to the converging series for now, and we will understand a little bit more about converging series tomorrow before moving on to Legendre polynomials. Okay, so I will stop for today, and if you have any questions, please do ask.